In this video, we'll discuss orthogonal decompositions. In this problem, we're given W, which is a span of two vectors in R3. We want to find the orthogonal decomposition of the vector V with respect to W. Let's start by drawing a general sketch which represents the geometry of the problem. So W is the span of two vectors in R3 which are not multiples of one another. So our two vectors might look something like this, and together they're spanning this plane. So let's call this plane here W. And we've got this vector V, which most likely does not lie in W. So let's draw V coming up out of our plane like this. To find the orthogonal decomposition of V, we're trying to write V as a sum of two vectors. We want one of those vectors to be in W, so maybe our first vector looks like this, and we want the second vector to be coming up perpendicular to W. So let's add a little bit of a description here. This first vector here, which is in W, that is called the projection onto W of our vector V. And the second vector here in our sum, which is in W perp, in other words, this vector is orthogonal to all the vectors in W. This guy is called the perp with respect to W of V, and the way we're going to find that is just by going V minus the projection. Alright, so let's see if we can find these two vectors, the projection and the perp. Well, first it might be convenient to give some names to our vectors in W. Let's call them W1 and W2. And we might notice here that looking at that set, W1, W2, these two vectors are orthogonal to one another, and that is great news. So we could say W1, W2 is an orthogonal basis for W. And I'm going to write a huge happy space beside that because that tells us that the projection is then going to be very easy to calculate. If you've got an orthogonal basis for a subspace, then to get the projection of any vector onto that subspace there, you're just going to project V onto the first basis vector. So we'll do V dot W1 over W1 dot W1 times W1, and then we'll project it onto the second basis vector as well and just sum up those projections. So just a caution here, incredibly important that we had an orthogonal basis for W. Otherwise, this method of just projecting onto each basis vector will usually not work. So let's take vector V, which is 4, 5, 8, and we'll do the dot product with our first basis vector, 1, 1, 1. That dot product is going to be 17. W1 dotted with itself gives us 3, and that is in the direction of W1. Okay, now projecting V onto our second basis vector, the dot product is going to look like negative 10. I'm going to erase this plus sign here and we'll just go minus 10 over dot product of W2 with itself is going to give us 14, and that is in the direction of that second basis vector 1, 2, negative 3. Alright, so I'm going to simplify this fraction here. Instead of saying negative 10 over 14, why don't we call it negative 5 over 7, and we can think about finding a common denominator here. I'm going to multiply top and bottom by 7. That's going to give us 119 over 21 times 111. And looking at our second fraction here, let's multiply top and bottom by 3. And then what I'm going to do is just leave everything over 21 but bring the numerator into the vector. For the second vector, again, we'll leave it over 21, but this time let's bring the negative 15 inside. So for me, this is the best way to prevent sign errors and any other sort of arithmetic errors. The projection is going to come out to 1 over 21 times the following vector. It'll be 104, 89, 164. So now at this point I'm going to erase this portion of the problem and we'll finish up by finding our perpendicular vector. So let's now find the perpendicular vector with respect to w of our vector v. We're going to take our original vector v and just subtract off this projection that we previously calculated. So we'll be taking vector 4, 5, 8 minus our projection. And just looking ahead at our next step when we're going to have to do this subtraction, I'm realizing it would be a little bit easier to introduce a common denominator right away. So instead of just writing v, why don't we call it 21 over 21 times v, and we'll speed up our next step of the calculation. So just like before, I'm going to leave the 1 over 21 out in front, just bring the 21 right into the vector. That's going to give us 84, 105, 168. And now keeping everything over 21, we can do our subtraction. So we're going to have minus 20, we'll have 16, and then 4. So we have now found two vectors, one which lies in W, and the other which is perpendicular to everything in W. We can check that these two vectors do indeed sum up to our vector v. And if you wanted, as a double check that we've done everything correctly, you could check that these two vectors here are orthogonal to one another. So really, it would suffice to ignore the 1 over 21 here and just check that the dot product of these two vectors is 0. That confirms that they are orthogonal to one another.